Hello friends, welcome to Net Chemistry. Today I am going to tell about organometallic chemistry in your GSI main exam topic. First paper, inorganic chemistry, you can find a topic called organometallic chemistry from this portion. It is very easy to score the marks. So you all should go through this organometallic chemistry completely. You cover the topic. All the direct questions you will be having. It is very easy to score the mark. Minimum 15 to 25 marks you will be getting from this topic. Okay, shall we start? Before starting into organometallic chemistry, first thing you should know about all the metals. What is the metals? D block elements, transition elements, all the elements you should know in the periodic table. So let us start with the periodic table. First is scandium, yttrium, lanthanum, copper, silver, gold, right? Zinc, cadmium, mercury. This is what D block elements. You should know first the D block elements and electronic configuration. Then only you will be able to answer the question. So first one is, this is 3D series, right? This is 3D and this is 4D series and this is the 5D series, right? This is the D block elements. Okay, here what is the electronic configuration? 4s2 3d1, right? 3d1 3d2 3d3. And here chromium, molybdenum, tungsten, if you are taking D4, actually it has to come because half-filled electrons will give you extra stability. So what will happen? It will become 3D5, right? 4s1 3d5 it will become, instead of 4s2 it will become 4s1 3d5. Then manganese, technetium, rhenium, if you are taking again 3d5 only, 3d6, d7, D8, right? Here copper, silver, gold, if you are taking copper, silver, gold, that also 3D9 it has to be. Then 3D10 will give completely filled orbital, will give extraordinary stability, so it will become 3D10. And zinc, cadmium, mercury 3D10, right? I am writing only first electronic configuration. Okay, here if you are filling it, it has to be 4D and here it will be 5D. Okay, this is the electronic configuration of D block elements. Now what is organometallic compounds? Your metal has bonded with a pi acid ligand, we will say. What is pi acid ligand? We will see first. Metal and pi acid ligand, this is what organometallic compound. Okay, what is a pi acid ligand? I am taking directly an example and explaining. If you consider the case of example, I am taking a carbonyl. Carbonyl means 6 plus 8 electron, right? 14 electrons are there. What is the electronic configuration of this? Sigma 1s2, this molecule I am writing sigma 1s2, sigma star 1s2, right? Sigma 2s2, sigma star 2s2. If it is up to 14 electron, you have to first fill pi orbital, right? Pi 2p x2, pi 2p y2, right? Then it will be sigma 2p z2, right? Then after that only pi star 2p x 0, pi star 2p y0, right? This is the electronic configuration of this CO, right? So what is the HOMO and what is the LUMO of this orbit, this CO molecule? What is the HOMO? HOMO is the highest occupied molecular orbital. That is what sigma 2p z2 is the HOMO, right? And what is the LUMO? Lowest unoccupied molecular orbital, that is pi star, right? This is LUMO. Okay, this is very important. What is the HOMO of carbonyl? Pi acid ligand carbonyl and LUMO of carbonyl. Okay, sigma 2p z2 is the HOMO and pi star 2p x0 and pi star 2p y0 is the LUMO. Clear? So this is the ligand we have taken. We know HOMO is sigma 2p z2 and LUMO is pi star 2p. This we have seen now. How this sigma 2p z2 will be forming? See, like this only bonding condition it will be, right? So this will join together, right? Positive lobes will join together. This is the way it is. Sigma 2p z2, sigma 2p z will be combining, right? This is what the molecular orbital is forming, right? So what will happen if it is bonded to any metal orbital? Metal orbital means d orbital, right? This is a doubly dumbbell shape, right? Positive and negative, right? And this carbon CO, right? CO and this is the 2p-Z orbital, right? This pi star orbital is here. This is the CO molecule, okay? CO molecule, if you see what is this electron density I have given, this is the sigma 2p-Z HOMO, okay? What will happen while it is bonding, metal carbonyls is forming, what will happen? This sigma electron density will flows to the metal. Then what will happen? Metal electron density will be increasing. So metal is having a tendency to decrease its electron density. What will happen then? Then metal is back donating these electrons to this pi star orbital, okay? This back donation is happening. So pi star is MD, right? Pi star is MD, 2px0, 2py0, both pi star orbitals are MD. So this extra metal electron density that will be receiving. See, if you see like this back bonding will be there, that like we will say a term synergic mechanism. What it is? So synergic mechanism. See, a ligand and a metal has bonded with a synergic mechanism. That ligand is called as pi acid ligand. So you know the mechanism of this back bonding or synergic mechanism. What will happen? Sigma 2p-Z electron density will flow to the metal. Metal electron density will increase, so that back donation will be there. So two question possibility is there. How CO can act as a pi acid ligand? Pi acid ligand means sigma HOMO will donate the electron and LUMO will accept the electron. This is the way CO will act as a pi acid ligand. And the second question is how CO can stabilize the low oxidation state of the metal. So how it is stabilizing low oxidation state means what it is low oxidation state? Low oxidation state means higher electron density, right? From sigma 2p-Z only higher electron density is coming. So how CO will stabilize? CO will receive the electron. Pi star orbital of CO will receive the electron. Another important term related to this topic is organometallic compound is 18 electron rule. What it is? 18 electron rule or EAN rule. What is 18 electron rule? With the metal ligand, if a compound is forming with metal and pi acid ligand, the metal should have a valency of 18 electron, then only that compounds will be stable. That is what 18 electron rule or effective atomic number rule we will say. So if it is a metal and a ligand is combining together to form a compound, this metal electron valency should be 18, then only that complex will be stable. That is what 18 electron rule. For that, predicting whether the complex is stable or not, and you should know how many outer electrons are present in the metal and how many electrons will be donated by the ligand, okay? So we will see this ligand, how many, we have seen only CO now, we will see the other ligands. Name of ligand I am writing, number of electrons donating by CO 2, right? If it is, this will donate 2 electrons. All the ligands I am writing, okay? This will donate 2 electrons. Dinitrogen complex, this will donate 2 electrons. If you see chlorine, bromine, iodine, all halogens, that will donate only 1 electron. If you see CH3, that will donate 1 electron. If you see CH2 double bond CH2, that will give 2 electrons. Pi orbital, 2 electrons will be there, that it will be donating. Here I would like to refer one more time. Hapticity we will see. See, like this only metal is bonding to CH2 double bond CH2. How many carbon skeletons are in equal distance from the metal? That is what we will refer the term hapticity. What we will say? Hapticity. Number of carbon skeleton equal distance from the metal. That is what hapticity, and it is represented by the term eta. Hapticity is represented by the letter eta. Okay, here it is eta 2. 1,3-butadiene. If you see 1,3-butadiene, it can bonded with the metal like this, right? Then the hapticity will be, number of electrons donated will be 2, and if it is bonded to metal like this, then it will be 4. Hapticity will be 4. And the same way you can take benzene. If you are taking benzene ring, this is the benzene ring, right? It can either bonded like this, that is 2 electron donor, or else it can be a 4 electron donor, right? Or else it can be a 6 electron donor, right? This is the way this organic compounds will be bonding with the metal. So what is the number eta? Eta is, can give 2, eta 3, eta 4. Based on that only you have to take how it has bonded to the metal, okay? If it is a benzene, You cannot take blindly, it will give 6, not like that. If it has given eta 6 here, eta 6 means it is donating 6 electrons. If they are giving the ligand and giving eta 4, then it will give only 4 electrons. Based on that only you have to choose your 18 electron rule. Okay, clear? So now I will write some examples. From that you have to find out the metal is obeying the 18 electron rule. Okay, first one I will write CrCO6. Okay, how to calculate the valency of, if the metal is obeying the 18 electron rule, metal valency should be 18 electron and then it will be stable. So we have seen chromium, how many electrons are there in the chromium? If you are taking chromium, it will be 6 electron, right? And CO6, each carbonyl will give you, carbonyl is 6 carbonyls are there, each carbonyl give 2 electrons, right? So it will be 12. So number of electrons present in CrCO6 is 18 electrons, right? Is it a stable compound? Yes. So we will see another example. Eta 5 C5H5 twice. What is eta? Eta is representing the hapticity. So eta 5 C5H5 twice. C5H5 is ferrocene. Ferrocene is donating 5 electrons to iron. That is what it is meaning by. So Fe, iron is having how many electrons? 8 electrons, right? Eta 5 C5H5 twice means 5 into 2 you have to do, then it will be 10 electron, right? So eta 5 C5H2 10 electron, 10 plus 8, 18 electrons. This compound is obeying 18 electron rule, right? This is the way you have to find out whether it is obeying the 18 electron rule or not. For that, what you should know, how many electrons are present in the metal you should know, and how much it will donate you should know. Okay, clear? Okay, now another thing is find out the metal bonds present. What you can find out with this 18 electron rule? Metal bonds. How many metal bonds are present in an organometallic compound? So what you have to do? I am writing an example, Mn2CO10. You have to find out the 18 electron rule. Whether this complex is obeying 18 electron rule, you have to find out. So manganese is having how many outer electron? 7 outer electron, right? 7 into 2 manganese are there. So you will be getting 14 electron. And CO is 10 COs are there. Each CO will donate 2 electrons. So you will be having 20. 20 plus 14 you will be getting how many? 34 you are getting. If it is a 34, it is not the multiple of 18. So what is the nearest multiple of 18? 36, right? 36 electrons should be there. Then only it will obey the 18 electron rule. If you are seeing here, manganese is having 2 manganese are there. So manganese, one metal bond will donate. One metal bond will donate 2 electrons. Okay. If you are adding 2 with 34, it is correct, right? 34 plus 2. 36 electron you will be getting, then it will be obeying the 18 electron rule. So how to find out the metal bond? This is the way you have to find out the metal bond. I will write one more example, then it will be clear for you. Fe3CO12 I am taking, Fe3CO12. So Fe iron is having how many electron? 8, right? And 3 ions are there, 8 into 3, 24, right? And CO is 12 COs are there, 12 by 2, if you are 12 into 2 you are taking 24. 24 plus 24 you will be getting 48. What is the nearest multiple of 18? 54, right? What you have to do? 54 minus 48 you have to do. You will be getting 6 electrons additionally you should require to complete the EAN rule, 18 electron rule. So what you have to do? This 6 electron, each metal bond will give you 2 electrons, right? Each metal bond will give you 2 electrons. So here 3 ions are there. 3 metal bond will be present. So 3 into 2 you will be getting 6. Now you can calculate, it is 54 electron. This is a multiple of 18. This complex is stable. How many metal bond is present? 3 metal bond is present. So one metal bond will give you 2 electrons, right? 2 electrons only can join together to form a one metal bond. This is the number of metal bond you can find out from this EAN rule. Okay, this is the another question. And one more thing I would like to say from this topic. See, if you are seeing ferrocene, you have seen, right? Fe, eta 5, C5, H5. This is ferrocene, right? In ferrocene, if you are seeing, it is 18 electron rule, it is obeying. 8 plus 10 equal to 18 electron it is getting, right? If I am taking manganese in, manganese eta 5 C5 H5 twice, okay? Manganese is having 7 electron, right? And this is 10 electron, right? Then it will be 17 electron. It is not stable, right? If it is a 17 electron, it required one more electron, then only it will become stable. So for what how it will be getting one more electron? It has to undergo reduction, right? It has to undergo reduction. Then only one more electron will be added to this, then it will be 18 electrons. So manganese always will undergo reduction. Now you see the case of cobalt acid. I am writing cobalt eta 5 C5 H5. If you take a cobalt acid, what will happen? Cobalt is donating 9 electron, right? Outer electron, all the metal outer electron I am writing, okay? Cobalt is having 9 electron. First itself I have written the electronic configuration. What is the electronic configuration of cobalt? 4s2 3d7, right? 4s2 3d7, so 9 electron plus eta 5 C5 H5 twice. So how much it will be giving? 10 electron, right? So totally 19 electron. This is also unstable. 18 electron has to come. This 19 electron, 1 electron is extra. So what will happen? Here it will undergo an oxidation, right? If it is removal of electron is oxidation. So this will undergo oxidation and removal of 1 electron will happen. This will be stable. So cobaltacene, manganesine and ferrocene, these three are very important, okay? So you know to find out the metal-metal bond, what is 18 electron rule. From this topic you will be having this type of questions will be there. And each ligand how many electrons is donating, that is the only thing you should know, okay? Clear this topic? Hope you understand it well. Thank you for watching.